Okay, I think we can start. Okay, so let's see. Last lecture we did this, so let's recall again. So we discussed the uniformization theorem. So basically, it said the following: if sigma is a simply connected Riemann surface, then one of the following three things happen, and only one of these cases. Then sigma is isomorphic to either CP1, this is a Riemann sphere, or isomorphic to C, this complex plane, or isomorphic to H. So this is the Poincare upper half plane with its complex structure. Poincare upper half plane. All right. So this is a trichotomy, and there's only one of these cases. It's a very deep and important theorem. There are many proofs now, but all of them are are quite difficult and rather deep, and they involve some great ideas. Okay, so I will discuss another version of this theorem, but let's see. Oh yeah, okay. So and one of the things that we have to know about these things or automorphism groups of these complex surfaces. So out of CP1 is isomorphic to PSL2C. This is projective linear transformations that act by Mobius transformations on the sphere. Automorphisms of complex plane. By automorphism, of course, we mean biholomorphism.
Is it PSL2C or just SL2C?
No, it's PSL2C. Yeah, because plus minus 1, multiply everything in a Mobius transformation by plus minus 1, changes the matrix but does not change the action. And we are caring about the action. So that's so it's a quotient of SL2C by this center, which is two elements. So the morphisms of C is affine of C. So this is the group of affine transformations of the complex line, which is, I just write it as Z2 AZ plus P, where AB belongs to C and A is different from 0. And the most interesting, of course, is automorphisms of H, upper half plane, which is PSL2R. You see, this is R, this is C. The dimension of this group as a real Lie group is 3, because you have 4 parameters, A, B, C, D, but then there's one relation, AD minus BC, which cuts it to 3. It's a Lie group of dimension 3. This is a complex Lie group of complex dimension 3 and real dimension 6. So CP1 is much larger symmetry in a way, but this is one.
Doesn't taking out the quotient of the center reduce even more the number of constraints?
No. That just is a covering map. it doesn't decrease the dimension because you are dividing by discrete group. And when you divide by a discrete group, it has no effect. If you divide by R or R plus or something bigger dimensions, as we'll see, that would decrease the dimension. But these are discrete groups. It's a covering one, yeah. Okay, now about this, let's look at this a little closer, see what it is. This H actually is a Riemannian manifold as well. So there is this hyperbolic metric on H. So this is our manifold, which is very simple, upper half plane. But there is a very interesting metric there, Riemannian metric there, ds squared equal to dx squared plus dy squared divided by y2. Okay? So this is a metric, Riemannian metric on upper half plane, which is conformally equivalent to Euclidean metric, but is not Euclidean metric. In fact, this metric, you can check that just using very simple Riemannian geometry that has constant curvature -1. So this is a metric of constant curvature -1. By curvature, in this case, I mean Gaussian curvature, which is the only curvature that makes sense in this case. A P equals to -1 to all P belonging to H. So, as you know, any Riemannian manifold also has an isometry group. So you can think of a group of its isometries that preserve the metric. And you may wonder, what is this group? And the beautiful answer is that this, so there's a theorem. It's actually not very difficult to prove. And the theorem is that the isometries of this group, and if you take only orientation preserving isometries, no reflections of H with respect to this metric, is exactly holomorphic maps. This is exactly PSL2O. Okay. So now PSL2O appears in two ways, either as a group of isometries of the Poincare plane, orientation preserving isometries, or the group of holomorphic maps from upper half plane to itself. And we'll see that this is not accidental because there is a relation between these things. Okay. So then we use this thing to construct. So now given for any Riemann surface X, so we can take its universal cover X tilde. So this is simply connected by definition and is a Riemann surface also. It inherits the structure of a Riemann surface. So by uniformization theorem is going to be one of these things, right? So uniformization theorem says that X tilde is one of these things. And in fact, X tilde is upper half plane if the genus of the surface bigger than or equal to 2. That's this is the genus 0 case. This is genus 1 case. I don't discuss this thing because these are easy. I just go to genus bigger than or equal to 2. Okay, X tilde is isomorphic to. Okay, so let me write it this way. Isomorphic to either CP1 or C or H. Okay, then what we did, we fixed the point on X. And then we looked at the fundamental group of the manifold at that point. Right? Okay, so then this acts on X tilde by covering transformations. Now, because we are in the holomorphic situation, this action is not just by deck transformations, which would be smooth. In fact, they are going to preserve the complex structure at the same time. So they really, if you really go into automorphisms of X tilde, so which is one of these three cases, right? Okay, now if X is closed, genus bigger than equal to 2, then we know what pi 1 of x and x0 is. So let me write pi 1 of x and x0 in general. So pi 1 of x and x0 then isomorphic to one of these three things, right? In the first case, it's going to be because this guy is simply connected and pi 1 is trivial, so it's going to be trivial. Trivial. In this case, we are dividing by some lattice, and then pi 1 is going to be isomorphic to Z2. And in the third case, which is the most interesting case, when you have a genus bigger than equal to 2, then pi 1 is a group that I wrote down. So it's a surface group, which is the group generated by 2G generators, A1, E1, AG, EG, such that product of commutators of AI, BI is equal to 1, I from 1 to G, right? Okay, so this, and in fact, there is an embedding here, goes to this. So then what we obtain is that Riemann surfaces are basically, okay, so let me put it this way, and pi 1 of x, x0 acts freely because it's deck transformations for the universal coverage acts freely. And there is a technical term which I won't explain it. I will explain it to you if you want to me after the class. Freely and properly discontinuously. So I will properly discontinuously. It basically means that if you have 2 points which are different from each other, there is actually neighborhoods around those 2 points that actually stay clear from each other on their orbits. So the orbits of the passing through these 2 different points never get close to each other. And this means that the manifold, the quotient space is hostile. That's a technical condition. And of course, in this case, we know that the quotient is hostile, so the action has to be properly discontinuous. So it's just a clean action, nice, very nice, the best possible action, so that the quotient is a manifold. Okay, so now what we obtain from here is that, in fact, basically a structure of all Riemann surfaces in some sense, right? Because now we know that they are obtained by quotienting either this or that or this by these subgroups of automorphism group that are, okay? So maybe that's why it's called uniformization, because it gives you a structure of all Riemann surfaces uniformly now in terms of, so all Riemann surfaces are obtained as quotients of. Well, anyway, in this case, there is nothing actually. In the case of CP1, since this is compact, there can't be any non-trivial subgroup that acts properly, that acts freely. I mean, any action would have a fixed point, and it's not good. So in this case, the subgroup is going to be just a trivial group. Just obtained as quotient of either C, okay, of CP1, C, or H. Why a nice, it means that free action and properly discontinuous subgroup. Okay. So what else did we do in the last lecture? Oh yeah, and I also said that we know what these things are actually. So definition, a subgroup, so a discrete subgroup gamma inside PSL2R called a Fuchsian group of first kind if this gamma for all gamma belonging to gamma different from identity, gamma is hyperbolic. I.e., absolute value of trace of gamma has to be bigger than 2. So remember, this gamma was ABCD, right? I mean, up to plus minus, because it's in the thing. So the trace of gamma, of course, is equals 3. Right? And what this kind of ideas show over there is that, in fact, for any Riemann surface compact X with a genus of X bigger than or equal to, you conclude that X is isomorphic to upper half plane divided by gamma, where gamma is one of these Fuchsian groups of first kind. I mean, this is gamma. It's Fuchsian. First kind. So maybe a little more about these hyperbolic groups, the properties of hyperbolic groups or hyperbolic elements. Lemma and gamma belonging to PSL2R is hyperbolic if and only if it has 2 fixed points which are on the real line or infinity. If and only if it has distinct fixed points P1 and P2 belonging to R union infinity, right? Where, I mean, this R is the boundary of H, right? This is basically boundary of A, like this. Yeah. Okay. So let me give you an example of hyperbolic element, an example of a non-hyperbolic element, so that you can see what's going on. So an example is gamma of z equal to 2z, or gamma of z equal to lambda z, lambda positive belonging to R. So just a quick thing. Y2z is a Mobius transformation, is in PSL2R. To z. If you write it, so if you write z,
its determinant is 0. Because we have 2 0 0 0.
no, to z you can write it as like this, right? 2 0 0 1.
Yeah. Oh, okay.
If you write it like that, then the determinant is 2. It's bad. So we don't want to take that representation. Yeah, we want to take another representation. 2z is equal to root 2 0 0 1 over root 2. You see, if you write it, I mean, right, because if you just follow this, you get root 2z plus 0 divided by 0 plus 1 over root 2, which is 2z. It's kind of confusing, actually, but this is not. You can do it with lambda as well. Right. Okay, so yeah, I'll let you think about it. It's kind of puzzling, actually. I agree. But let's see, what are the fixed points of this? Fixed points of gamma. Well, there are 2 points. One is 0, and the other one is infinity. Is 0 and infinity, which is here. And in fact, how it acts, there is one point which is here. It's kind of repelling. Everything goes away from, every point multiplied by root 2. This stuff. And at infinity, and it basically pushes everything towards infinity. Right? And there is a geodesic, in general, there's a geodesic that connects P1, P2. So, okay, I mean, in this case, this is the geodesic that connects 0 to infinity, but in general, P1, P2, because we know that in the hyperbolic plane, there's a unique geodesic that connects P1, P2, and that's the semicircle that's orthogonal to the line at these 2 points, right? So we just take this. And it turns out that this Mobius transformation, the hyperbolic ones, keep the geodesic intact. It doesn't change. And this is kind of analog of translations along one straight line in Euclidean geometry. So there is a perfect analogy with Euclidean geometry, but it needs a little bit of thinking to go through all the analogies. So the geodesic arc A, gamma of A is equal to A. This is the arc A. In this case, it's also a geodesic. It's, obviously, this line, this geodesic line, is also mapped to itself. Right. Now, but examples of non-hyperbolic elements, I mean, you can construct non-hyperbolic. I mean, you can, for example, look at rotations around any point. They keep one, they have a unique fixed point. And so let me write it. So, for example, if you get this point, I, there is this cosine theta, I mean, sine theta, negative sine theta, cosine theta. I mean, okay, so this is fixing. Yeah. So this is an element of SL2R, right? Because cos squared plus sine squared is 1, determinant is 1. It's also a rotation. So okay, maybe I don't want to discuss this now. So let's don't turn into hyperbolic geometry course. This is not.
Are these points called hyperbolic because they throw points out of the center?
Yeah, because exactly, because with respect these 2 points, which are fixed points, they send one to the other one, and the whole thing goes either to this one or the other one. So this is the idea of hyperbolicity. Yeah.
Sorry, what exactly is being sent? What I don't understand.
What? Sorry.
Sending what? What is being sent?
Oh, the under the map, because the map acts
Oh, I see.
on the upper halfway,
I see.
right? So this geodesic, for example, is sent to itself. It
Oh.
moves the geodesic, but sends to itself.
Yeah.
P1 goes to P2, P2 goes to. So these are like analogs of lines and translations along this line. So the line is not. Okay, so oh yeah, so that's let's not lose track of things. So then what I promised to do is heuristic argument for dimension of this modular space to be 3G minus 3, or dimension of G, which is dimension of TG equal to 3G minus 3 over C, of course. If dimension of G, I mean, if the genus of G is big enough equal to 2. This G is the genus. So why we have this now? Because it's highly non-obvious fact. I mean, where this number comes from. So we approach it through this argument here. So what is that? So basically, all Riemann surfaces are uniformized. Okay, so we know that. So argument is the following. All Riemann surfaces of genus bigger equal to 2 are of the form upper half plane divided by a Fuchsian group gamma of first kind. But the gamma basically is a group that has two G generators and one relation because of fundamental group of the manifold, right? So gamma is isomorphic to the group generated by A1, AG, B1, BG, which I had over there, by the way, and product of AI, BI, I from 1 to G equal to 1, right? So basically now the question is, how many such subgroups, what is the parameter space, dimension of a space of all such subgroups? Okay. So how can we construct such subgroups here? What is the freedom? So yeah, in physics, they have a very good concept. It's called degree of freedom of the problem. So we have to understand the degree of freedom of this problem, and that's the number of parameters that you need in order to describe your system, basically, the system, the problem, right? So how many degrees of freedom we have? Well, you see, you can choose this A1, AG, B1, BG completely arbitrary inside PSL2R, right? So choose A1, AG, B1, BG completely arbitrary in a PSL2R, except for this condition, right? Okay, for each of them, you have how many choices you have? You see, for each parameter, you have three choices. I mean, 3 degrees of freedom, because ABCD, a matrix in ABCD is fixed by 3 numbers. So you have 3 degrees of freedom for A1, 3 degrees of freedom for B1. So you have 6 degrees of freedom for A1, B1. And then you have another 6 degrees of freedom for A2, B2, and so on. So basically, you have 6G degrees of freedom. Right? 6G degrees of freedom. You have. So then, what are the constraints? You have one constraint, which is this one, but this is a matrix equation. So it subtracts three parameters for you, because this is really 3 equations, not 1 equation, right? Because this is a matrix equation. This 1 means 1, 1, 0, 0. So you subtract 3. Now, where the other 3 comes from? Well, the other one is because this is not quite given by that, because everything speaks up to conjugation. If you conjugate the group by any element of SL2R, then you're going to get the same group, which is isomorphic to the original one, and you get the same Riemann surface. So that cuts down another 3. So this is because of conjugation. This one is because of constraint star. So total, we get 6G minus 6 degrees of freedom. And which is complex 3G minus 3. 6G minus 3 is complex 3G minus 3. So so this is really related to this guys. Amazingly, this number was known to Riemann, actually. Riemann writes this. And I believe he even coins the term moduli space, but something like that, I'm not sure. But he has a count for that. His count was different, was not through this method. And he used another method. I believe he used Riemann-Roch theorem, which maybe I will discuss later on, but no. Okay, so that's what comes from this picture. Okay. Now, I want to give another angle on Riemann surfaces, which is, oh yeah, before we move on, let me give you a subgroup which is not hyperbolic. Yeah. A non-hyperbolic. So that is non-Fuchsian, right? So good. And so when you think about discrete subgroups of PSL2R or SL2R, the first subgroup that comes to mind is what? What is the first subgroup? If you want to think of discrete subgroup of SL2R, what subgroup comes to your mind? Okay, so let me give you an example. If you want to think of this discrete subgroup of R, what example comes to your mind?
Z.
Z. Yeah, this is the quintessential discrete subgroup of R. But there are many others. You can multiply, for example, Z by some positive integer, a positive real number, you get another discrete subgroup. But this is kind of example. But there is an analog of this for PSL2R, which is SL2Z. So you look at SL2Z. But this is discrete. But this is not hyperbolic. In fact, I mean, you can construct elements. I mean, for example, let's look at this element, T of Z. Equal to Z plus 1. So T is this matrix, 1, 1, 0, 1. So it's a translation. It's not hyperbolic. Yeah, you see, this has only one fixed point, which is the point at infinity. So the fixed point of this guy. So it's move everything. In fact, the quotient here is not compact. I mean, if you take C, I mean, H divided by this PSL to Z is so this is this domain, right? So let me this one, sigma. Of course, you have to identify this line with that line and that line. So this is called modular curve. After you identify, so this looks like something like this. So there's a cost point. So I mean, these 2 points actually in the metric approach to each other, and there's a cost point at infinity, but it never closed. I mean, this is the modular curve, which we know what it is actually. This is the modular space of Riemann surfaces of genus 1. So, but the point is that it's not compact manifold, compact space. It's a because of such cost limits. Yeah. Right. Okay, so I didn't see what time is it. Okay, not much time. Okay, so now I want to open another angle to uniformization of this thing, which is basically a relation between Riemannian metrics and complex structures. That's also very important. Okay, so basically, the Riemannian surfaces versus Riemann surfaces. So here is Riemannian surface, right? I mean, this is a Riemann surface. I mean, there are different things. So let me give you the definition. Okay, so a Riemannian surface sigma and G is a two-dimensional smooth manifold equipped with a Riemannian metric, right? So G, I mean, so these are like we have even n-dimensional analogs of this thing, Riemannian manifold in general. But the Riemann surface, of course, is a two-dimensional. I mean, it is a surface equipped with a complex structure, which is. So the question is, what is the relation between the two concepts? I mean, if I have, is it true that if I have a Riemannian metric on G, I can endow on sigma, I mean, I can endow sigma with a complex structure, or vice versa? Is it true that if I have a complex structure, I can endow it with a Riemannian metric? This sort of things. So to answer this question, I introduced a concept called conformal equivalence. The definition is conformal equivalence. So the idea is that the matrix G1, G2 on sigma are called conformally equivalent if there exists a function h, smooth function h from sigma to r, such that G1 is equal to e to the h G2. I mean, this is like in physics, so this conformal equivalence matrix. So, I mean, the thing is, you can say this as a positive, multiplied by a positive function. The only thing is that this function need not be constant, so it can the scale can change from point to point. So this is called conformal equivalence. I mean, this is obviously an equivalence relation. And if you divide the set of metrics by this equivalence relation, each equivalence class is called a conformal class. Okay? So
what is e to the power h? What is e to the power h?
E to the power h is a function. It's a function, and these are tensors. So it means that this tensor is a multiple of this smooth function times this tensor. H is just this one. So this is called the conformal factor. Is that okay? Okay. So then a conformal class is just an equivalence class like that. So then what we can do, we can just, so let R sigma, okay, so let conf sigma be equal to R sigma mod out conformal equivalence. So R sigma is the space of all Riemannian metrics on sigma. So now what we want to show is that basically this space conformal metrics, space of metrics up to conformal equivalence. So here's the proposition, is that this space is in one-to-one correspondence with complex structures on sigma. So complex structures are really conformal classes of metrics, complex structures. On sigma. Let me tell you how this works. So to see this, we'll sketch. We need to see a few things. We need to know a few things. First of all, there is a lemma which is in complex, so I call it lemma 1. So this is in complex analysis, and it's very elementary. It basically says that if you have a conformal equivalence between two domains, if f from U subset of C to B is conformal equivalence, I mean, so let me, not conformal, this is a bad term. It's actually, it's a biholomorphism. Biholomorphism. And then you can say two things about this. First of all, it's orientation preserving. F is orientation, then one, F is orientation preserving. And the second one is that F is a conformal map. I preserves angles. So Biholomorphism between domains need not preserve metric, but is conformal, preserves angles. And this easily follows from Cauchy-Riemann equations. Just to prove Cauchy-Riemann equations. Implies that actually the Jacobian the matrix of this one, Jacobian of f at the point xy is of the form ux uy minus uy ux. If you write the Jacobian in terms of u and v, then you can write it in terms of this one. So where f of z equal to u of xy, v of xy. Just write the Jacobian. So then, first of all, the determinant is positive, and is also up to some scaling. It's an orthogonal map. You can divide by norm of this matrix, and then you get this orthogonal map. So it's the following: it's an orthogonal transformation and the scale. This is conformal. So this is elementary. But lemma 2 is not elementary. It's something that actually was first discovered by Gauss. So this is Gauss 1820s. And it just says that any two-dimensional Riemannian metric is locally conformally flat. Let me write it like this. Locally, a two-dimensional Riemannian metric G equal to G mu dx mu dx nu, right? Because it's a complicated 2x2 matrix, which is positive, definite, and all that, right? It's a two-dimensional. Locally, it can be written in a very special form. Is locally is conformally flat. So what does this mean? Conformally flat means that there exists a coordinate chart in which G is actually of the form e to the h times dx squared plus dy squared. Coordinate chart x and y in which. So you can, here the metric, it looks like you have 4 degrees of freedom in the metric, right? Each component is a function of two variables, but in fact, there's only 1 degree of freedom, which is this h, which is conformal factor. I mean, this has practical implications. It's not an abstract result. It means that any two-dimensional surface, and you can always construct a map of a two-dimensional surface where angles are preserved, locally at least. So this is a map-making problem that motivated Gauss. And actually, there's a very, very interesting story behind it. Gauss knew the solution because in around 1790s, they discovered that the Earth, I think French and others, discovered that the Earth actually is not round. So that gave them a big problem, and namely, okay, so if the Earth is not round, how we can construct maps of Earth where angles are preserved? Is it possible at all? So Lagrange proved that if the Earth is still a solid of revolution, it's taking any curve, special curve. If it is a solid of revolution, then such maps exist. But then the question is, well, it's not be like that. It could be something even more crazy. Can we construct such one? So this is kind of abstract question, but it's motivated by some map making issue. And Gauss showed that such a thing. Gauss knew how to prove. Okay, in Gauss's proof, he had to prove that he had to assume that these functions are analytic. But then then it was proved using more advanced techniques 100 years later that the solution also exists in the same category. And so Gauss was kind of was acting in a particular way there because he knew the solution, but an Academy of Science of Denmark asked him to propose a problem to be given as a prize question to kind of encourage research in this area. And Gauss gave this problem as thing. So they waited for 2 years. There was no solution. So Gauss gave his solution.
And did he get the prize?
I don't know. Perhaps it. I don't know. So these are things you study in history of mathematics. So you go to libraries and investigate, find archives, find some letters that was lost and all this.
They give a problem for which you know the solution and get the prize.
Seems like a bit.
But Spain, right? They waited for 2 years. No one could come up with something. Give the solution. So then I'm going to use next time. I'm going to use these two facts to prove that actually, this statement is true, and this is our link between Riemannian metrics up to conformal equivalence and complex structures. I mean, this one. Sorry, this one. This is more or less, this is the definition. This is, I think today is 1 hour, right? Okay, if there are no questions, I should say goodbye then. Are there any questions? No, look like there's no questions. Okay, bye guys.